All right. David Rice is a PhD candidate at the University of Nevada, and we will be hearing about his open source planet interior structure code. So take it away, David.
Hi, everyone. Thanks for coming to my talk, and thank you for the organizing committee and everyone who organized this great conference. And hi, if you're watching this afterwards also. My name is David Rice. I'm a PhD candidate at the University of Nevada, Las Vegas. I work with Professor Jason Steffen, and I'm going to be talking about MAGRATHEA, which I co-authored with Chenlang Huang, who's now a faculty at Shanghai Observatory. We'll be talking about solving and visualizing planet interiors. So if you've looked at an observational paper recently, these are the most recent, like 15 planets that have been characterized their mass of less than 10 Earth masses on the Exoplanet Archive. You'll see a section in one of those works where they put their planets on a mass radius diagram and compare it to some curves of isocomposition, and putting these planets into context of what they might be made out of. But if you've looked into how you draw these lines of constant composition, these interior models can become quite complex. So these are two recent interior models to study the interiors of planets from Acuna 2021 and Dorn and Lichtenberg 2021. And these are all the works that inform their interior model. And the tree structure here is because not all of these works are even cited in the top level paper, color coordinated by which layer it informs. If we could camp out here for long enough, we'd see there's very little overlap between the two works also. They're using entirely different high pressure material geology works to inform their interior models. So the community is really in need of a flexible, well-documented, and widely available planet interior model. So welcome to MAGRATHEA. MAGRATHEA is our open source planet interior platform hosted on EMAC. It's written in C++, takes about 1 second to run a planet. It's fully extensible, so as long as the equations behave, we'll give you what your planet might be, what might be happening inside of your planet. But the equations are best behaved for terrestrial planets. And we'll be talking about how it's really transparent for phase diagrams and equations of state storage. And when we're talking about interior structure model, we're talking about a 1D spherically symmetric, fully differentiated shell model generally. So these were first used for exoplanets in the early to mid 2000s with the works listed down here. And what these models do is they solve the equations of hydrostatic equilibrium, including an isentropic temperature gradient. You put the mass into each layer. We have 4 layers: an atmosphere, hydrosphere, mantle, and core. And the code outputs the radius, pressure, density, and temperature, all those interior conditions that you might want to know about your planet. And I call it a shell model, but you can think about this also as we want to input some kind of composition, but also within each layer, interior models become more complex for planets because we want the pressure and temperature conditions to tell us what actual materials are being used. So within each layer, we have a phase diagram. So these are our default phase diagrams for our hydrosphere, mantle, and core. We got hexagonal closed packed iron in the core, along with liquid iron, these different phases of magnesium silicate in the mantle, along with silicate melt, and water in different phases of high pressure ice in the hydrosphere. And for each one of these, why we have so many works that go into these interior models is for each one of these works, we want to understand how these materials respond to pressure and temperature. So ideally, we would crush them in a lab with a laser heated diamond anvil cell shown here at the bottom to understand how they respond to pressure and temperature to give our equations of state and also our phase transitions between all of these different materials. So on the left here is a Birch-Moynihan third order equation of state. This is just one kind of fitting formula that high pressure physicists use to describe these materials. Important here is the bulk modulus. This is how resistant the material is to compression, or 1 over the squishiness. And we have 7 different equations of state parameterizations in the code. So you might have a Birch-Moynihan third order for your Bridgmanite, but you might have a Binet equation of state for your post-perovskite. You want your code to shoot right through those and solve those equations of state. To show how important these equations of state can be, let's imagine some fun planets first. These are the planets from Douglas Adams' 1979, or Hitchhiker's Guide to the Galaxy. Hitchhiker's Guide to the Galaxy describes this mystical planet where they build other planets, and that planet's called MAGRATHEA, and they talk about building a gold planet and a platinum planet. So we had fun and put a gold equation of state and platinum equation of state in the code. And if you imagine a 1 Earth mass gold planet and a 1 Earth mass platinum planet, which planet would be bigger? The question. Well, you might think your gold planet would be bigger because gold is less dense at low pressure. But if you look at the equation of state, you find that gold is squishier than platinum. So gold quickly becomes denser inside of the planet, and the platinum has a larger bulk modulus. So your platinum planet ends up being about 2% bigger than your gold planet for a 1 Earth mass planet. And this is a fun example, but this can really matter for different measurements for the same material even. So here's the only slide with the actual code in it. This is our equation of state storage structure for 2 measurements of iron, hexagonal close-packed iron from a 2013 work and a 2017 work. You can see they use different fitting formulas, a Hall-Zeffel and a Binet equation of state. And with those different fitting formulas and their different data, the bulk modulus is cut in about half. And in the code, we have over 40 different measurements for planet materials and measurements for those different materials. So shown here is a plot from our work where we have 100% composition planets with on a mass radius diagram. You can see different measurements for the same exact material can create planets 2% difference in radius. But then if we talk about like putting silicate into the core, so our iron silicate alloy, that can create planets up to 5% difference in radius. I want to highlight that we have new measurements from UNLV physicists. That was our original idea with the code, is they've crushed some new water ice and had a new equation of state, and we wanted to model planets with it. I also have undergraduates. This is undergraduate week can get up on this code and put in some new materials into their planets. So what you get out of MAGRATHEA is this kind of symbolizes all the functionality of MAGRATHEA. You put in this differentiation for 1.1 Earth mass planet. You can also put temperature discontinuities between the layer. We have a jump in a conductive layer between the core and the mantle and the Earth. And over on the right, we see the output for this code. For this planet, and you can see as our enclosed mass increases from the surface to the center, the temperature follows the isentrope. We pass through liquid water to ice 6, to ice 7, to ice 10 as the pressure increases, into bridgmanite into the mantle, post-perovskite in the mantle, and the hexagonal closed pack iron in the core. On the left here is a blender output. I have a high schooler working on taking MAGRATHEA outputs and putting them into the 3D animator blender, so that's going to be a really fun, useful addition to MAGRATHEA. The rest of the talk, I just want to show some things to inspire you on what you might want to do with an interior solver. First, you might want to make mass radius curves for your work. So this is actually a bulk density with planetary mass plot. And the lines here are drawn with MAGRATHEA for 100% core, 100% mantle, and 100% water planets. And we see our confirmed small planets of less than 10 Earth mass with some uncertainty cut off on their masses and radius really span this area. So we have planets all the way up here at the 100% iron line, and planets that require some volatile layer or require an atmosphere on them. And you can draw these mass radius curves in just minutes with MAGRATHEA, with the most up-to-date equation of state from the literature. You might also want to make ternary diagrams. So this is a water mantle core ternary diagram. Ternary diagrams are a lot of fun to explain, but every point on this plot is a different differentiation in mass between 4 3-layer planets. So these are all the different radiuses you can get for a 3-layer planet of 1 Earth mass. So down here at the bottom is our classic Earth, 1 Earth radii would be around this 33% core to mantle ratio. But as we increase the core mass, we also have to increase the mantle mass to keep it at that 1 Earth radius. These are all the possible radiuses for the planet. You can make a ternary diagram in just an hour. My favorite thing to do with MAGRATHEA, and what I'm working on now, is to characterize planets. I do this in McDonald 2022, but now I've been working with TRAPPIST-1F, this amazing measurement from EGLE 2021. Our smallest uncertainties are mass and radii. This is all of the possible interior structures for TRAPPIST-1F. So this is taking 5,000 draws of mass and radius, shooting across reduced core mass fraction, which is a core divided by the mantle, and then solving for the water mass fraction, or it's the core divided by the mantle plus the core, kind of the iron to silicate ratio of the planet. And you can see the different water mass fractions across this parameter space, and an Earth-like RCMF we require about 6.5% of water. We can also ask if it has no water, how can you recreate TRAPPIST-1F? And we find that you need a 14% plus or minus 3% core mass fraction for the planet. This takes about 500,000 runs of MAGRATHEA, and we have it in a multi-thread mode, so you can run this across 12 cores, and it'll just take about a day. We have a ton of future development we'd love to do. This is my laundry list, and this would be great projects for undergraduates, for graduate students to jump on board with MAGRATHEA. We're finalizing that compositional finder. We're improving the water layer, including a supercritical water and coupling with the aqua group of equations of state. We want to do ideal mixing in the layer so we can do some iron in the mantle, non-ideal atmosphere, three-dimensional PVT tables for tabulated equations of state, coupled to an atmosphere model, coupled to a thermal model, coupled to SPH so we can do planet collisions between fully differentiated planets. These are some things we'd love to do with the code, and we'd love to see other people from the community jump on board. So you're welcome to become a MAGRATHEan and join us modeling planets. Thanks.
Awesome talk, David. Really cool program that you're developing here. If there's any questions for David, please feel free to raise your hand or post them in chat or on Slack. I think I see one on Slack here. It says, this might be science fiction, but can you estimate can you make estimates about the presence of surface water?
Yes, definitely. Some planets like TRAPPIST-1F has this tantalized. TRAPPIST-1F is 10% less dense than the Earth, even though it's very similar to the Earth mass and radius. So one explanation for that is it has a hydrosphere. And we see in our solar system, we have planets like Ganymede with 50% of this mass and a water layer. So I'm very optimistic about super Ganymedes. I think they are a thing that fits our demographics currently, and we'll see how it fits in the future. So just from their densities being low, we can estimate that it might have a hydrosphere, and then from their temperatures, coupling with one of those atmosphere models from earlier in the day would be great to understand their possible surface temperatures.
Awesome. Looks like Eric, do you have a question?
Yeah, just real quick. Dave, I'm really impressed by all the functionality you built into that, getting out the ternary diagrams, everything else. I was curious when you said something like TRAPPIST-1F could take up to a day. I was just curious, what is sort of the limiting feature in those run times? And I wonder, could there be a mode to run it with slightly fewer MAGRATHEA threads, for more quick explorations?
Yes, of course. So that was with 5,000 posterior draws of mass and radius, and then running it at integer RCMF, or this refractory core mass fraction. So the paper I'm working on, we actually determined that 2,500 is better for this planet to characterize it. So that cuts that time in half. You can do it at every other RCMF. That'll cut your time in half. Also, if you really want to do planets fast, we have an isothermal mode. So this is with isentropic temperature gradients within the planet. You can turn off your temperature, so it's just the same temperature throughout your planet, which for a lot of planets doesn't change their radius by a large amount. And then the code takes it's like 100 times faster in the isothermal mode.
That makes sense. Thanks.
Great. Well, my first question is, why didn't you show the picture of all those plots on top of each other from your first slide?
Yeah, that's the very first slide. It's the most low effort Twitter post ever. If you want to follow me on Twitter, it is MAGRATHEA staff. I named myself on Twitter before I named the code. So
It's awesome. This is really cool. I'm just excited to dig into it. I guess we have a couple minutes here. Is there any restrictions in terms of installing it, or any things that users should know? As I myself will probably be downloading it here in a couple of hours to check it out.
hey, would love that. I held a workshop on it at Rocky Worlds this summer. So I have a little workshop if you want some practice problems to go through with it. It's written in C++, but our input file is, I think, very easy to understand. I've got undergrads who have never coded before working with just that input file. So don't let the C++ scare you. Creates a faster code in general. It does require GSL. That's the only prerequisite. So, and there's some problems with downloading GSLs, especially on M1 MacBooks. We have problems with those too. So we've been commiserating with your problems with WebEx.
Yeah, that sounds great. Well, thank you again, David. And if anyone else has any questions, please feel free to post them in Slack.